All right, let's get started. Day 9. Okay, interesting. Easy to parse, that's for sure. Yeah. Okay, now we're the whole way with amphipods. I don't remember this one. Oh my god. Okay, that's scary. All right, so we have a disk map puzzle input. Disk map uses dense format to represent a layout of files and free space in the filter. Files and free space on the disk. It teaches alternate between indicating the length of the file and length of free space. Interesting, okay. So disk map 1234 would represent one block file of free space. Okay. 3 block file. Oh, no. One block file, 2 blocks of free space, 3 blocks of file, 4 blocks of free space, and then 5 blocks of file. Okay. The disk map like 9090 would represent 3 9-block files in a row with no free space between them. Interesting, okay. Each file on disk also has ID number based on the order of the file as they appear before they are rearranged, starting with ID 30. So the disk map 1234 has 3 files. A 1-block file with ID 0, a 3, then there's 3-block file with ID 1, 5-block file with ID 2. All right, so far so good. Okay, and then representing it, okay. Disk map 1234 represents these individual blocks. The first example above represents 3 individual blocks. 2s, then 3's empty, 1, 3's, no, 3, 3, then 2, 1 empty, 1 file, 3 empty again. Okay, no, that checks out. Okay. The amphipod would like to move file blocks one at a time from the end of the disk to the leftmost free space block until there are no gaps remaining between five blocks. Okay, so we move, or is this, oh, this is from here. For disk map 1234, the process looks like this. So zeros, wait, why would they move 2? From the end of the disk to the leftmost free space block. Well, that seems easy enough, okay. But ignoring the first group, interesting. So 9. Oh, okay. All right, seems easy enough. The final step for this file compacting process is to update the file checksum to calculate the checksum. Add up the result of the multiplying each of these blocks' positions from the file ID number it contains. The leftmost block is in position 0. If a block contains free space, skip it instead. There could be empty space. Okay, so continuing in the first example, the first few block position multiplied multiplied by its file ID numbers are. Okay. Oh yeah. Okay. Okay, hold up. What do you mean first few blocks? Zero times zero, zero, 1 times 0, 2 times 9, 3 times 9, 4 times 8. Yo, this is gonna be bad. So hold up. No, not bad, but like, if I take this D, right, and then, so this is the answer, right? Iota, right, so 1, 2, 3, 4, 5, times input itself, 0, 0, 18, yeah, okay. Sum it all up, 19, 20. Yeah, maybe it's not like a lot. But what does skip means? If a block contains free space, skip it instead. If a block multiplying file ID to calculate the checksum, it'll just be 0, right? We'll just mark it 0. All right. So this is our score calculating function. We'll do it later. Move it to the end here. All right. So how big is the production one? Just thinking, 20,000. That's not that bad. It's not that bad. So we'll do brute force. Maybe there's a better way, but yeah. Now, what we need to figure out is how much. All right. So we got n, and essentially I mean, I don't want to add up the whole thing. Oh, the one in here is 94,000. If I add up, wait a second, 94,000, 20,000. Yeah. All right. So we can just build this whole thing and, all I really care about at the end is that the so presumably, so this is a perfect shuffle, right? Basically, right? 9, 9, 8, kind of perfect shuffle. All of the free space yeah, then we reshape n like that, and we divide it into, no, I don't like this. We don't reshape it like that. Modulo 2. Ooh. 2 times, no, yeah, reverse this, right? So we got the IDs, we multiply them by the thing, so we have that, and then we just multiply by 0.5. So we have the groups like this. The ones in the middle, we'll just pretend that they're zeros, right, for now. And then split it up like that. Kind of similar, right? Except 0 is, we could, okay, to make it a little better, this, right? And 2 equal times I, right? So we'll just, instead of the actual ID, like 0, 1, 2, 3, we'll have a 1 incremented, because we want to skip the empty ones. We'll reserve 0 for empty, right? And then now if we do that, okay, so now imagine we increment it, right? So 1, 1, why am I getting, I still need to divide by 2. Multiply. Yeah. And then checking. Yeah, okay. So we're just using 1 incremented IDs. So instead of ID 0, we'll use ID 1, and then for free space we'll use 0. Right? So we'll just increment it by 1. Okay, so this is what our underlying data looks like. Yep. And so that's the disk, right? Now for disk, we find zeros, right? And is that the right way? Yeah. Count how many there are. And 14 zeros, right? We will, so they warned us that there could be a gap at the end still, so that's possible. But okay, let's just try it one thing at a time. So we have this much free space. So where, so we can take n, again. No, D. Remove zeros. And now we can subtract 1 from it, just for convenience. Right. We reverse it. Oh, we don't reverse it. Yeah, we do reverse it. We do reverse it. Right, and we take this much, right, till A6. There should be at least 1. 6, something's wrong. 9, 8 gets put in here, right? No, 9, 9, 8 gets put in there, right? Then 8, 8, 8 get put in there. 8, 8, 8 goes put in there, okay. Then 7, 7, 7 get put in there. Then another 6, and 1 more 6, and 1 more 6. 6, 6, 6. I feel like we don't have enough 6s now. Yeah, we didn't move any 5s. Hold up. It gets folded onto itself. Right? Right. It's not that we just inject. Oof. Okay. No, we can do that. Okay, we can do that. How did this happen? 8. Oh yeah, okay, okay. There's no gap here because that was a 0 there. Okay, that's fine. So we can just keep taking from the end, recursively in a while loop, and putting it at the first. Yeah, let's just do it that way. Okay. So we have our D, which is something similar to this, except all the IDs are incremented by 1, and 0 means that it's an empty space, right? Then we can take one loop, right? So it will take the last, well, does it have any empty space? If it has any empty space, it does. If it doesn't have anything, then we just return, right? In our case, we do. So 42, yes, we do, okay. So we take the last item, that's going to be a 10, which is really a 9. And we need to put it where the first index of the first 0 is, which is going to be rank error. What are you talking about? It's the other way around. Right. The first index of a 0 of an empty space is at position 2, 0, 1, 2. That's correct. Yeah. And that's where we place. So in a W, omega, at this position, we place the last item, and we drop one, the last item at the end, obviously. represent it like I did before. So there's actually a dot, 0, 1, 2, 3, 4, 5, 6, 7, 9. Okay. All right, took 2 seconds for some reason. Yeah, so 8, 8, 8, 9, okay. Power 2, 3, 4, 5, 6. Yeah, we want to get rid of trailing. They're like a trailing. Come on, trailing ones. Count of trailing ones. What is that? Boolean, okay. Yeah. Okay. All right. So hold up. I have 1, 0, 1, 1, 0, 0, 1, right? This will trailing that one with itself. That's a 1, okay. What if there are no, okay. If I have 1, 1, 1, 3, okay. All right, pretty cool. So if I took the input, which in my case is this, I will need to, so that's the new D, all right. Then we check for zeros and we count number of the zeros at the end and we negate it and we drop this much from the data. So now, there you go, there's no trailing thing at the end. Oops. There is no trailing dot. Okay, so 8, just run it till it doesn't move anymore. There you go, okay. And then 0, 9, 8, okay, cool. And then this is our formula that we use here. So we need to, there are no more zeros anymore, so we increment it by -1. Now it's back to normal, and we use our formula to figure out the cost, which is 1928. But hold up, I think I did something wrong. The leftmost block is in position 0. If a block contains free space, well, that's the one, yeah, so there will be free space. We got rid of it, so it doesn't matter to us. 1928, if I run it for real input, it took a while. Put it in. Yeah, okay. Let me run it again. Is it really that slow? Oh my goodness. We might need to optimize it for part 2. Okay. So 2 things become immediately clear. Disk definitely has a lot more contiguous free space, just like the amphipod hoped. Second, the computer is running much more slowly. Maybe introducing all of that fragmentation was a bad idea. The eager amphipod already has a new plan. Rather than move individual blocks, he'd like to try compacting the files on disk by moving whole files instead. Oh, snap. Okay. This time, attempts to move whole files to the leftmost span of free space blocks that could fit the file. Attempts to move each file exactly once in order of decreasing file ID number. Okay, so we have, okay, attempt. If there is no span of free space to the left of file that is large enough to fit the whole file, the file does not move. Okay, so we have 3 spots right here, And the last one is 9, 9, so it fits perfectly. Then next one is one space, and 8 is definitely not going to fit there. So where's 8 going? 8 is not going anywhere. Interesting. 8 just stays there. Okay, the next one is 7. 7 goes in here. Oh my, okay. 7 goes in here. Extracting it a little bit. Okay. By the way, the first part could have been done much simpler, I feel like, but it works. I'm not gonna touch it. Maybe optimize it a little later, and I'll comment it out for now because it adds a 1 second to the runtime. First example from above. Okay, so 7 goes in there. Next one we have 3 spots. 3 spots. Who has 3 spots? None of these fit, so 4, 4 fits in there. Okay, first one that fits was 4, 4. Next one, 1 spot, nothing. Next one, 4 spot, nothing. Next one, no, what? Yeah. Wait, it just keeps on moving. Next one is 4, this spot, nothing fits here, right? This 4. We don't try 8 anymore. We don't try 8 anymore. Yeah. And we move, so we actually end up moving 2 all the way to the end if there's no span of free space, to move each file exactly once in order of decreasing file ID number. Okay. Yeah, that makes sense. Yeah, so we just run from 9 till 0, right? And yeah, that part is simple, I think. So I'll comment this out, start a new one. So we have our D, no, what is D? D is the input here, right? Okay. Then we maybe we should start with N actually, but probably not. Yeah, no, we'll start with D. Yeah, okay, so here's what we'll do. At each step, right now, let's say we need a 10. I mean, this part is easy, right? We just figure out the unique numbers here, remove a 0, right? So these are all the unique numbers, and we reverse the order. But we actually don't need to reverse the order because I'm going to do the reduce, which works from the right to left. So this is fine. Yeah, so we'll have this part is easy. So we have a 10, and we have our digit thingamajig, right? So we have a 10. Now we want to count how many 10s there are. How many 10s there are? How big is this group, right? Size of 2. And we try to find the first position where 2 will fit, right? So that's how much we need, size. Then we, let's not try to make it a one-liner for no reason. a little higher. Yeah, this will be the input. And by the way, the input will be this together with the D. But anyway, okay, so we and then we just reduce it. But one thing at a time. We have the S here, right? Now next one is so we have the size that of our thing. Let's check if the input has contiguous groups. Where can we find a contiguous set of things? So take this, we group it into the thing itself, right? So these are all the contiguous okay, I have a better idea. So so these are all of the ones. So we need to find where so let's say we need 2, right? So we need to find where we can fit a 1, 1, right? So we can use an E exists and it will tell us 0, 1, 2, right? Wait, the other way around. The other way around. Exists 1, 1. Basically, we need to find the first one where it fits. Where can we fit 1, 1, 1 in these positions? Where can we fit 4 ones? Nowhere. And it's true. In the beginning, there's nowhere we can fit a 4 block of ones. Yeah, okay. So S replicated 1, yeah, or 1 replicated S times, which of course is this, but let's see. All right, and we find the first one. Is that the way? Reverse it. This is the first place where we can fit it. There's the first index of the first one. Let's just fits, right? If fits, that's a 1 exists and fits. If 1 does not exist and fits, we return our input as is, right? In our case, it does exist, so it errors out. Then we find index of the first one, yeah, and we want to place it at that position. And how do we do that? We take this many of iota how many S, right? So we have S number size number of positions. So we create a iota. So again, we have two spots that we need to fit. So S becomes our thing, position 0 and 1, and we just need to offset it by this many, by that position, right? So at position 2 and 3, we need to create, so at input in this position, in these positions, we want to put in our number. So what is our number, by the way? 10. Yeah, 10. Well, Yeah, which is 9 really. So we fit it right here. Okay. So cool. That seems to work. So if I do the same thing, but reduce, and I need to disclose. Yeah. If I put a 9 in there, right? 9, which is, yeah, 9 went, which is an 8. Didn't move. And of course we need to remove the original number from it. There you go. So 10 got removed. 10 got removed, but something's wrong. Hold up. Yes, that's not what we do. We don't just remove these blocks. That will shift things around. So where A and alpha are the same at those positions in input, we put a 0, right? Do I need this anymore? Yeah, I don't need this anymore. Okay. Yeah, all right. So then put a 9 in there. So we ask to move 9, which is an 8. Doesn't get moved, right? We try to move 8, which in our map is 7s. So this 3, 8 to the end. They get moved in there. And so 4th. What about 7, which is a 6? 6 doesn't get moved. Yes. 6 in ours, which is a 5 there, doesn't get moved, still stays there. 5, which is a 2 4s right there, they get moved. And 5 4 just go all the way. 3 does get moved, which is a 2 does get moved. Yeah, 2. Okay, why doesn't 0 get moved? Shouldn't the 0 get moved all the way here? And that's my thinking. So 3 gets moved. 2, which is a 1, doesn't get moved. But in our situation, it does get moved. We move a 1 as well, all the way here. Is there anything about moving it to earlier? Okay, so I'd like to try compacting the files on the disk by moving whole files instead. This time, attempt to move whole files to the leftmost span of free space. Oh, okay. So leftmost. So what we could actually try to do is need to calculate the fits. And if the fits is okay, yeah, so we need to check if it's actually moving to the earlier place or later one. We want to go to the leftmost. What did you say that just now? Leftmost span of free space. So this didn't get moved because there is no space earlier than 8.8 except for its own position, and you can't just move it by 1, right? We couldn't have done that. But 0 or even a 1 1, 2 got moved, 2 does get moved because there's something earlier for it, but 1 doesn't get moved like here for no reason because the leftmost is itself. If there is no span of free space to the left of a file that is large enough, yeah, to the left of the file. Okay, so we just need to check that this position that we're trying to move it to actually is is actually earlier than the number itself. All right, so for that, I will just go back to 9, right? No, not 9. Well, yeah, so the hell, just return I. Right, in this case, it doesn't work. Let's do 10, right? So 10 is a position at position 2, but let's check if where it itself is, I keep mixing it up, 40. 40. It is at position 40. If I is more, right, than this position, in this case, no, we can move it to the earlier one, and we return W or omega as is. So now, when we try to do 9, it doesn't get moved, 10 got moved, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Let me try just with a 1, which is our 2. 2 got moved. No, wait, 1 is a 2, and 0 doesn't get moved. Perfect, okay. 0 doesn't get moved, and then I just need to still print it. So 0, 1, 2, 3, 4, 5, 6, 9. Press print it. So 2 9s, 2 1 7 space 4 space 3 3 bunch of space 5 6 8 is as is. Okay. The process of updating file system. Okay, so now, awesome. And I believe it's just this, right? Nope, messed that up. Is not the same thing. One, two, three, four, five, six, 10, 9, and D. Yeah. Oh, comma, closed. There you go. So it should be this. Yeah, okay. So we reduce let me just rename it index. There you go. Okie dokie. Feel like there's a better way to do this part, but okay. Anyway, we get the result, and then we still do the same formula as before, which is our sig, which is not gonna work because it doesn't handle empty spaces well. And the way we do that is, so we have, we remove all the ones, we subtract 1, right? And then No, we don't subtract 1. We don't subtract 1. So we take the length, multiply by, no, we take the length iota, multiply by this -1. Oof, no, that's not gonna work. That is not going to work. Maximum 0, there you go. 2858, yeah, so if it gets below 0, then good. Yeah, okay. For real one, oof, why is it so slow? Hopefully it finishes, because it's a reduction. 11 seconds, my goodness. Okay, we got, that's the right number. But it's really slow. Let me run it again. Let's see if it actually is slow. I wonder, we can profile. Let's profile. Where is this? Profile, there you go. 11 seconds, my goodness. So the way we profile is, let me get rid of this. So this is part 1. Let's do part 2. I'm curious which part is so slow. Obviously it's not the signature, obviously, or is it? Yeah, okay. So we should be able to profile like this. So whatever function that we call, well, our function will get called many times. Yeah, that's fine though. So this will be our reduce function. I don't know. That's the best I can do for name. And except we will profile it, calling it R. Think that should do it. Yeah, so this just, didn't I name it? Oh. What? So it's a special function that takes as a inner operand, is a inner right operand, a name. I have no idea how that works. So profile is a function that takes the things. No, it must take R as well, like this. Undefined R, what the hell? Where's that coming from? Ah, right, because we assign it. All right. Ooh, why are you printing so much? No, don't print it every time. Okay. Yeah, it doesn't like that we call it so many times. So we'll have another function that actually does this, and it takes, so solve, right? We'll call it solve, and it calls R. D will be the input, and we solve for D, and except we profile it, and we profile both signature and R, right? Something like that. So we profile signature on R, we solve, we call the actual function on the D, which will be running slower now. Okay. So 10,000 times, which I guess makes sense. That's how many inputs we got. Okay. Signature is fast somehow. That makes no sense. Hold up. We profile OCS, ODD, and even. And instead of just calling OCS, we call it with input and a function, left argument. Think something. Okay. It doesn't like signature. All right, doesn't matter. So which part is slow? The slow part will be 96% of the time is taken on the fits. All right. Is it because of the E? Probably. Because there's no way this is slow, and there's no way, what's going on here? One reduce of that size, it's going to be like maximum 9. So this part is fast. So we're looking for spot of size 9. And this E will check it everywhere. We just need the first one. We just need the first one. First block where it fits. Let's split it up. Let's just double check. So this will be A, I don't know. This will be B. Then A, B. Take 12 seconds, but I imagine the part that's slow is the exists in, or whatever it's called. It will be slow because it will try to fit it into. Yeah, this part is slow. We just, because it finds all of them. It will find all of them, and we just need the first one. Okay, so how can we do this better? Oops. Oh, so given a 0, no, we have, I don't know, 1 1 0 1 1 1 0 0 0 1 1 1. Another one here, I don't know. Yeah, and this is a Boolean matrix, right? We're looking for 3, right? This is essentially our B, right? B says, hey, we need, give me all the zeros. So here you go, all the zeros. Now we need to group it. So grouped into itself. That work? Yeah. Display. This is not optimal. Running. Is there a running contiguous contiguous. First ones of each group of ones, no ending point of group of Boolean gaps. Ending points, length of subvectors having equal elements, length of groups of ones. Yes, I think this is what we kind of want. We have a Boolean matrix. What the hell does this do? 2 4 3. All right, cool. The hell does this do? 243, 243, but that doesn't give us the index. Doesn't give us an index. Right. Let's say we see this 4. Okay, great. Now where is this 4? It's right here, but that doesn't tell us anything about where it can fit. Right, yeah. All right, I can probably optimize this part, but this will take a lot of time, and it's unlikely to be that. I think like the proper way to solve this is to use like more complicated splitting rules where we don't keep like 20,000 array, whatever it is, 50,000, 40,000 array blocks. We just have some sort of reference. How can we represent this kind of thing, honestly? And we need to do some sort of splitting. So for example, when we have a 9, where is this? Right here. When we have a 9 right here at the end, we know that there's 3 spots right here, and it will just be represented as just 3, right? And we would take that 9, we will have like 2 9s somewhere, and we would put it into the place where we have a 3 and break it into 2 and a 1. Yeah, this could work. Okay, interesting. All right, so I solved it already. We know the solution. I don't want to commit this. It looks ugly. You know what? Maybe I will commit this. Let me run this. So this is all out, and undo all this splitting our business. Undo. Remove the profiling. Remove all of this business. Come on. So where did the reduction? Okay. Is this the right one? Yeah. So 1 works and 2 also should work. Real slow. It would, okay, yeah, so it works. I will commit this as original, as initial. Boom, okay. 09 and in 29, 24, 24, 9. Slow. '18 in 17. Yeah, but there must be a better way. There has to be a better way. So I think I need to implement this kind of like splitting behavior. So for that, I will get rid of all of this. Not very useful. Signature will also be different, so I don't need signature. I can always recreate it again. The model, the representation model that we'll have is, I think, what is our? It's definitely not D, right? That's just bananas. What about N? What is N? Okay, no, that works. Yeah, that works. Yeah, I think we'll have numbers. So these are groups, right? We'll call them groups. Groups. Or or sizes. These will be sizes. I don't know. And it's fine. And it's fine. So these are the groups. Now, and we'll have well, maybe I kind of want to get that original code right here, but I'll only keep part of it. So don't want to do this. Yeah, there you go. So this is the same thing. Yeah. So if I don't print this for now, so n will be our numbers, right? So two sizes of the groups, right? And this will be the name of that particular ID group, right? Except it's one incremented, right? So if it's a 0, that means we have a it's an empty free space. If it's a 1, it's really a 0. If it's a 10, it's really a 9, etc. So right here, we have two groups of 10, no groups of 0 of empty space, 4 groups of 9, 1 group of empty space, etc., etc. 2 groups of 1 right here. Okay, so that checks out. So we'll operate with, this will be called groups. All right. So N and G will be my two special yeah, something like that. Will be the special, that's a representation. So for part 2, we go from the end as well. We'll probably do a reduction. And still, but this will be the data structure, right? NG. And at each point, we try to reduce, yeah. So let's say this is our representation, right? And we have a 10 that we want to, well, yeah. We have a 10 and this N and G, right? So we, for part 2, we want to split up. Yeah, I'll spend maybe 5 more minutes and then I'll finish this a day later. Time outside the stream, I know I'm time boxing it 1 hour. So I'll spend maybe 5 more minutes on this. I think this is the better solution ultimately. But okay, so we have a 10 right here. Yeah, 10 is what we're looking at. And where is it? It's right here. And how big is it? Easy. So honestly, I can just probably update N and G. No. So N and G will be omega. Number is alpha. So alpha group number in alpha 18. Yeah, makes sense. Count will be number in the number array. So if we return C will be 2, right? So it's size 2. Now we're going to look for n where it's at least count. Yeah, all of this fit. Perfect. Right? Yeah, so we have they all fit too, except where, so and the groups themselves are not 0, right? Not 0. So these are all possible locations, and we'll positions that we can put things in. Okay, or candidates. And if position, if one doesn't exist, I always confuse. There you go. If one doesn't exist, if this is, if the index of the first one wait, if one I already forgot. Yeah, these are Boolean matrix, right? Boolean matrix. If they are not, if there are no, I don't know, this is confusing. If one doesn't exist in here, then we return input as is, we're not touching anything, right? But in our case, it will fail, right? Because we do have it. So what is the index of the first one that fits? And this is the part that was slow in our original solution, finding that first fit, right? It was we were using this operator. It was really slow. So in our case, fits into hold up. We're looking for space position where it is 0, right? We need to find an empty one. So in our case, there you go. In our case, it is position 1, but position 1 has how big is that position? 3, right? So we have to split it up into, so we know it was an empty space. So now we make it an, we need to insert, here we need to insert something. This is like linked list. If I had linked list, that would be nice. Because what I'm trying to do here is, so into n, we need to inject at position. So at here, we need to inject. So we're always, maybe we don't need to worry about it too much. I can compress it. Yeah, we don't have anywhere where it says it has to be alternating. Okay, so we need to inject a at this position we need to inject numbers will be 2 and 1, right? Split 3 into 2 and 1, right? So it was a group of 3 empty spaces, and we splitting into a group of 2 and a 1, and at a group of this position, we need to split that group of empty space into, now it's a 10, well, alpha, and a 0, right? Oh, that's not that bad. That is not that bad. Yeah, that should work. Okay, I'm going to check out. I will try to do this offline. I think it's doable. It might be still slow, right? Because we're injecting, splitting things up here. And then we need to compress it potentially. Does it make sense to compress? If we don't, can we, what if we assume that it's an empty space? That there's always an empty space following the a contiguous block of whatever, right? What if we assume that we have that? Then, so we know this is an empty space, right? Now, oh no, that doesn't really help, right? This is an empty space. We need to take the empty space and convert it into empty space, then the block of the thing that we're moving into that spot, and then empty space again. Okay, so we cannot assume that we have alternating free space and not free space. Yeah, all right. Yeah, all right. My worry is that the splitting behavior will be slower because we're moving the whole two arrays, right? And we're shifting it by one. So that's not optimal. That is not optimal. If we had a better data structure, that would be really nice. Yeah. All right, I'll think about it. I'm worried about this splitting, and then at some point I'll need to like compact, right? We need to compact contiguous, whatever, contiguous groups of 0, right? So if you have a bunch of like group of zeros, like 0, 0, 5, 3, 2, whatever, then it needs to combine into one. Would that actually, does that matter? Can we? Yes, we can. It could be. No, that doesn't actually matter. I was thinking like this 4, 4. No, it could be. So this 4, 4 got moved. Yeah, but if we're moving this 4, 4 again, okay, let's just step back. So we move 4, 4, right? So now we have group of 1, and potentially this will be another group of 2 that's empty space, and then another group of 1 that is empty space. So technically we have a group of 4, but in our data structure it will look like 3 groups of empty space of 1, 2, and 1. And we'll not be able to fit anything in there. But I'm just thinking like if I move this 4, 4 to a left or more position, so we have this gap, that means the next number we're looking at is going to be left to it. So it's going to be 3, 3, and we're not going to be putting 3, 3 into this contiguous space. So we don't care about this. We don't care about compacting. So compaction is not that important. What about here when we yeah, what about here? What was part 1 again? Yeah, part 1 is where we had 9, 9. So technically here, what would we be doing? Would we be going one at a time maybe? So every time we see a 9, or like whichever is the last one that we haven't looked at, we take that, whoops, and we put in the beginning, which we split. Technically it's the same as part 2, except when we see a 9, 9, we're like, hey, it doesn't matter, put it in there, right? When we see 4, 8, we just distribute it across all of the positions that we have here. Yeah, that might work. Alrighty, it might work. I'll think about it. We have our initial solution committed and pushed, just not here anymore. That's fine though. Size, yeah. Yeah, anyway, thanks whoever was watching. Have a good day, have a good Monday.